Imagine a world where NVIDIA, a company known for its calculated moves, suddenly changes its playbook. For years, they have been a fast follower, letting others pioneer the riskiest new manufacturing technologies first. But what if, for their 2028 Feynman GPU architecture, NVIDIA decided to lead the charge? Picture this. NVIDIA becomes the first major customer to embrace TSMC's groundbreaking A16 2-nanometer process node. This wouldn't just be an upgrade, it would be a declaration. It signals a fundamental shift in the semiconductor world, where the insatiable demands of artificial intelligence, not the yearly churn of smartphones, dictate the pace of innovation. This hypothetical leap is more than a technical decision. It's a strategic power play with massive implications for the entire tech landscape. This move would be a significant departure from NVIDIA's established strategy. Traditionally, the company has preferred to wait for a new process node to mature. They would let others, often Apple, absorb the initial costs and risks associated with early adoption. This allowed NVIDIA to benefit from improved yields and a more stable manufacturing process for its massive, complex GPUs. However, the AI boom has changed the rules of the game entirely. The demand for more computational power is growing exponentially, and incremental gains are no longer sufficient to maintain a competitive edge. A decision to be the first on TSMC's A16 node would signal that NVIDIA sees AI acceleration as the primary driver of semiconductor progress, a responsibility it is willing to take on directly. The stakes are incredibly high. For NVIDIA, leading the adoption of a cutting-edge node means shouldering immense financial and technical risks. The initial wafers from a new process are notoriously expensive, and yields can be disappointingly low. Any delays or manufacturing hiccups could disrupt their entire product roadmap, giving rivals a golden opportunity to close the gap. Yet, the potential rewards are equally monumental. If successful, the Feynman GPUs built on the A16 node could deliver a generational leap in performance and efficiency that competitors simply cannot match. This would cement NVIDIA's dominance in the lucrative data center and AI markets for years to come, creating a moat that is nearly impossible to cross. This isn't just about building a faster graphics card, it's about defining the future of computation. The very architecture of AI models is co-evolving with the hardware they run on. A massive leap in GPU capability, as promised by the A16 node, could unlock new types of AI that are currently beyond our reach. It could accelerate scientific breakthroughs, from drug discovery to climate modeling, and power the next generation of autonomous systems. NVIDIA's choice, therefore, isn't merely a business decision. It is a bet on the direction of technological progress itself, a move that could either propel the industry into a new era of innovation or serve as a cautionary tale about the perils of moving too fast. To understand the gravity of this potential shift, one must look at NVIDIA's history. The company has built its empire on a foundation of strategic patience. Consider the progression of their architectures. The Pascal GPUs used TSMC's 16-nanometer process, a mature node at the time. The subsequent Turing and Ampere architectures leveraged TSMC's 12-nanometer and Samsung's 8-nanometer nodes, respectively, both of which were refined versions of existing technologies rather than brand-new, unproven processes. This approach minimized risk. By letting other high-volume players like Apple iron out the kinks in a new node, NVIDIA could focus its resources on architectural design, ensuring their complex chips would manufacture with reliable yields and performance from the start. This pattern continued with more recent generations. The Hopper architecture, a powerhouse for data centers, was built on a custom version of TSMC's 4-nanometer process, which was an optimization of the 5-nanometer node. Similarly, the upcoming Blackwell architecture for 2024 is expected to follow this trend, likely using another refined variant of an existing TSMC process. This fast follower strategy has been incredibly successful. It allowed NVIDIA to deliver consistent, powerful products without exposing itself to the extreme volatility of early-stage manufacturing. The company's massive GPUs, with die sizes far larger than a typical smartphone processor, are already challenging to produce. Adding the uncertainty of a brand new node would multiply that challenge exponentially. The rumored Feynman architecture for 2028 would break this long-standing tradition. By targeting TSMC's A16 2-nanometer process from the outset, NVIDIA would be placing itself at the bleeding edge of semiconductor manufacturing. This is a role usually reserved for Apple, whose massive iPhone volumes help TSMC finance the development and ramp-up of new nodes. For NVIDIA to step into this role signifies a seismic shift in priorities. The relentless demand for more powerful AI accelerators has seemingly become a more potent driver than the annual smartphone upgrade cycle. The incremental performance gains offered by mature nodes are no longer enough to satisfy the hunger of large language models and complex AI workloads. This historical context is crucial because it underscores the calculated nature of NVIDIA's potential decision. This isn't a reckless gamble, but a strategic response to a changing market. The company has seen the future, and it is powered by AI. To maintain its leadership position, it can no longer afford to wait in the wings. It must take control of its destiny by driving the manufacturing roadmap itself. This leap to the A16 node for Feynman would be the most aggressive technological step in the company's history, a clear signal that the era of conservative node adoption is over, and the era of AI-driven semiconductor leadership has begun. TSMC's A16 process represents the next frontier in semiconductor manufacturing, a technological leap that promises to redefine the balance of power, performance, and efficiency. Scheduled for production in 2026, the A16 node introduces two game-changing innovations: nanosheet transistors and backside power delivery. Unlike the FinFET transistors used in previous generations, nanosheet transistors feature gates that wrap around the entire channel, providing superior electrostatic control. This drastically reduces current leakage, allowing for higher performance at the same power level or significantly lower power consumption for the same performance. For a power-hungry GPU, this is a revolutionary advancement that could enable unprecedented computational density in data centers. The second key innovation is backside power delivery. Traditionally, the power delivery network and the signal network share the same intricate web of wiring on the front side of the chip. This creates routing congestion and signal interference, limiting performance. With backside power delivery, TSMC moves the power rails to the back of the silicon wafer, creating dedicated pathways for power. This frees up the front side exclusively for signal interconnects, simplifying the design and allowing for more direct and efficient connections. This separation is expected to boost logic density, improve signal integrity, and enhance power delivery, leading to a significant speed improvement and better overall chip performance. From a performance perspective, the A16 node is a giant leap forward. Compared to TSMC's N2P process, an enhanced 2-nanometer node, A16 is projected to deliver Media Group, side-by-side bar chart of chip speed improvements, engineer pointing at performance metrics on screen, close-up of chip with nanometer measurement overlay at stock, edit distribute underscore equally, a 15 to 20% speed improvement at the same power, or a 30 to 35% reduction in power consumption at the same speed. It also promises up to a 1.1 times improvement in chip density. For a massive AI accelerator like NVIDIA's Feynman, these numbers are transformative. It means more cores, higher clock speeds, and greater energy efficiency, all within a single package. This would allow NVIDIA to build chips with trillions of transistors that can train and run next-generation AI models faster and more economically than ever before. However, this cutting-edge technology comes at a steep price. The cost of designing and manufacturing chips at the 2-nanometer scale is astronomical. Mask sets, the stencils used to pattern the silicon, can cost tens of millions of dollars, and the price per wafer is expected to reach new heights. This makes the A16 node economically viable only for high-margin, high-performance products like flagship smartphone processors and, crucially, data center AI accelerators. The immense cost creates a high barrier to entry, concentrating power in the hands of a few companies, like NVIDIA, that have the financial resources and market demand to justify such a massive investment. NVIDIA's potential move to the A16 node is not happening in a vacuum. It is a direct response to the intensifying competition in the AI hardware market, particularly from its arch-rival, AMD. Under the leadership of CEO Lisa Su, AMD has transformed from an underdog into a formidable competitor, mounting a serious challenge to NVIDIA's dominance in the data center. AMD's Instinct line of accelerators, such as the MI300 series, has gained significant traction by offering a compelling combination of performance, memory capacity, and an open software ecosystem, ROCm, which really appeals to customers seeking alternatives to NVIDIA's proprietary CUDA platform. This growing threat is, well, forcing NVIDIA to become more aggressive. AMD's strategy has been to compete fiercely on both performance and value. While NVIDIA has historically commanded a premium for its GPUs, AMD has often positioned its products as a more cost-effective solution without a significant compromise in capability. For their next-generation products, AMD is also expected to be an aggressive adopter of advanced process nodes from TSMC. If NVIDIA were to stick to its traditional, more conservative, fast-follower strategy, it could risk falling behind. A scenario where AMD launches a product on a more advanced node ahead of NVIDIA could erode the performance advantage that has long been NVIDIA's primary selling point, making this a critical moment for strategic decision-making. This competitive pressure is likely the primary catalyst for NVIDIA's potential pivot. The company recognizes that in the fast-moving AI space, maintaining a significant technological lead is paramount. Simply keeping pace is not enough. It must create a gap that competitors cannot easily bridge. By being the first to market with a GPU built on the revolutionary A16 process, NVIDIA could re-establish a commanding lead. The performance and efficiency gains from the new node could be so substantial that they would render competing products from the same generation obsolete before they even launch. It's a high-risk, high-reward strategy designed to checkmate the competition. Furthermore, the battle extends beyond just the silicon. It's about the entire ecosystem, from hardware and software to networking and system design. NVIDIA's advantage has always been its mature and comprehensive CUDA software platform, which has a deep moat built over more than a decade. However, as competitors like AMD improve their software offerings, and as more open-source alternatives gain traction, that moat is no longer impenetrable. By pushing the hardware frontier so aggressively with the A16 node, NVIDIA would be reinforcing its primary strength. It would create new hardware capabilities that can only be fully unlocked through its tightly integrated software, forcing the ecosystem to continue building on the CUDA platform to access the best performance. The decision to pioneer the A16 node for an AI accelerator carries immense manufacturing and testing challenges. At the 2-nanometer scale, the physics of chip-making become profoundly more complex. The transistors are so small, composed of just a few dozen atoms across, that quantum effects like tunneling become significant problems, causing current to leak even when a transistor is switched off. Verifying a design before committing to manufacturing becomes an incredibly difficult task. The simulation models must be exquisitely accurate, as even the tiniest discrepancy between the model and the physical reality can lead to a non-functional chip. The sheer complexity of a GPU with trillions of transistors magnifies this challenge exponentially. Manufacturing itself is fraught with peril. The process relies on extreme ultraviolet lithography, a technology that uses incredibly short wavelength light to etch the patterns onto silicon. At 2 nanometers, the precision required is honestly mind-boggling. A single stray particle, smaller than a virus, can create a fatal defect, rendering a multi-million-dollar chip useless. Early production runs on a new node are notorious for low yields, meaning a large percentage of the chips produced are defective. For a company like NVIDIA, which produces some of the largest monolithic dies in the industry, low yields are a financial catastrophe. This risk is why companies have historically preferred to wait for a node to mature before using it for their most complex products. If NVIDIA successfully navigates these challenges, the impact on the industry could be profound. It would mark the official transition of technological leadership from the consumer mobile market to the enterprise AI market. For the past decade, Apple's iPhone has been the primary driver for TSMC's most advanced nodes. If NVIDIA's Feynman GPUs become the flagship product for A16, it would signify that the immense computational demands and high profit margins of AI are now the main engine of semiconductor innovation. This could, change how foundries prioritize their research and development, tailoring future nodes to the specific needs of high-performance computing rather than low-power mobile devices. Ultimately, NVIDIA's move is a monumental bet on the future. If they succeed, They could redefine the AI industry and solidify their dominance for the next decade. The Feynman GPU could become a legendary product that unlocks new possibilities in artificial intelligence. However, if they stumble, if the yields are too low, the costs too high, or the technical challenges insurmountable, the consequences could be severe. It could create an opening for AMD and other competitors to seize market share, and it could serve as a stark warning about the risks of overreaching. The question for the industry to ponder is whether this is the dawn of a new era led by AI, or a risky gamble that could reshape the competitive landscape in unexpected ways.